This? Hello, hello. Hi. Oh, shit. Hello, testing, testing. Is it good? Even if you speak this direction? Good. Yeah. Yeah. Hello. Well, thank you. So thank you, the organizers, for the opportunity to be here in Atlanta giving this tutorial. So it's my first time here, so I'm quite excited. And thank you, Sivas, in particular, who has been my point of contact, and to Monique as well, who has helped a lot with all the hotel flights and everything. So has been great. So as Siva was saying, my research is basically in this crossroads between statistical physics and machine learning. And I guess there are two kinds of tutorial that I could have chosen to give. One would be about results that we can derive using statistical physics methods, which, as Siva was saying, usually as a physicist trying to make contact with the machine learning community, we try to kind of hide how we derive some of these results, and we try to go directly into the proof, and everything is a bit opaque. So I could have given a tutorial about some recent progress that we have made in understanding, let's say, neural networks. But what I have decided instead is to try actually to go into the part that we hide and try to motivate a bit this connection. So it's going to be kind of a two-box tutorial. And one of the reasons I have decided to do that is that part of the machinery that we use in this field is related to actually the other tutorial by Cynthia that you're going to be having also in this school. So I'll try to make this connection, and you're going to see how it goes. So it's a bit open-ended. I have some lecture notes from a previous course that I have given last year in Princeton. So I'm going to try to follow more or less that. And we are going to see up to where we get. It depends on the interactions. So please don't hesitate to ask questions. So when I gave this course last time, there was a lot of questions, there was a lot of back and forth. So I prefer to have that and maybe cover less material rather than just go at full speed and cover everything. Making sure everyone is on board, especially if you're not used to this connection, which I'm assuming most of you are not. So please interrupt if there is anything if there is any language that I'm speaking that you don't understand, make sure to interrupt me and ask, okay, can you clarify what is a Boltzmann distribution, for example? What is a free energy? And this kind of stuff, right? So please feel free to ask questions, to interrupt. I'm happy to have a discussion. Okay, so this topic, I guess most of you are aware that has been growing, has been getting more and more place within the statistical physics and machine learning community. And in particular, in the past 5 years or so, there has been like 4 big awards given to people that worked directly into building this connection between statistical physics and machine learning. So the first one was by Giorgio Parisi, a Nobel Prize in 2021. Giorgio, who's in the University of Rome, is one of the main drivers of this field on the physics side, fields which we call like sometimes as spin glass physics or disordered systems, which is a subfield of statistical physics. So he was awarded the Nobel Prize for deriving some of the tools that we're going to be studying here in this tutorial. Then there was the Abel Prize to Talleyrand. I guess Talleyrand is more familiar to most of you. So Talleyrand was essentially the mathematician who tried to make sense of Giorgio's results and prove a lot of results in high-dimensional probability in the context of disordered systems. So much more recently, in the past year, there was another Nobel Prize to John Hopfield and Geoffrey Hinton. And so Hopfield was one of the first actually to make the connection between neural networks and statistical physics. We're going to see more about that later today. And Hinton, let's say, even though he's not a physicist, he has also got a lot of inspiration in his work from physics and statistical physics in particular. And the Nobel Prize last year was awarded jointly for both of them. So just to clear out maybe some confusion there is, especially when we talk with physics about this connection between these two fields, I'd like to quote one interview that Hopfield gave after the Nobel Prize about what is statistical physics. And the question that he was posed was, there was a discussion that your prize-winning work was not really physics, but actually computer science. So what do you think? And which he answered, my definition of physics is that physics is not what you're working on, but how you're working on it. If you have the attitude of someone who comes from physics, it's a physics problem. And that's a great quote because I guess for people coming from computer science, that's more natural, but actually within physics, our old school way of thinking about physics is that physics is about the nature, right? You're studying molecules, you're studying gravity, you're studying things which are natural phenomena. But actually, when you talk about statistical physics, it's started studying nature, but the tools which were developed are much more universal. The language of statistical physics is the language of complex systems, and complex systems can be everywhere, can be in biology, you can study the DNA, and in computer science. So what the point that Hopfield is making here is that statistical physics is a state of a spirit and not a field specifically. It's a way you think about a problem and not the problem itself. So if you think like a physicist, that's statistical physics about a given problem, whether it's in computer science or a natural phenomena. And this tutorial is exactly about trying to think as a physicist on computer science problems. And in particular, we're going to consider the problem of complexity, computational complexity, and we're going to consider the problem of machine learning. And hopefully, towards the end of the lecture, you're going to use the tools that we're going to be introducing today to actually think about these two fields within the same language. So you're going to see already that the tools are quite universal. Once I start making the introduction of some of the tools you're going to be using, these tools can either be speaking about Bayesian inference, can be speaking about typical case computational complexity, or about empirical risk minimization. all within the same kind of a framework. Okay, so let me just try to state a little bit my goals for this tutorial. So I guess most of you come from computer science. I don't know if you can read the first one, but okay, my goal for this tutorial is that, okay, if you are from computer science, you know nothing about physics, like the base goal is that you understand this connection and you can appreciate, you know, that statistical physics can be a useful way about speaking about problems in computer science. Now, for a fraction of you, I expect that you really enjoy the methods that we're going to be speaking about, and you'll also be able to read papers from people that come from this part of the community, and who knows, maybe collaborating with some of your physicist friends on problems in machine learning and computer science. Finally, for a tiny, tiny fraction of you, maybe, I hope that you appreciate that so much that you want to learn more, dig more, learn, like, you know, pen and paper, the details of these techniques, and who knows, maybe use this on your own research. And then maybe for one of you, you'll say, who cares about computer science and machine learning? Spin glass is a very cool problem. Let me work on statistical physics of disordered systems. And change department, okay? So, okay, that's a joke. I guess that most of you are PhD students, so I don't want to be responsible for your supervisor then searching after me and say, what did you do with my students? So, okay, ignore the last one, but at least the 3 first ones, I hope that's what I expect for this tutorial. So let me just give you a little bit about what is the plan. So for today, most of today, my plan is to go through a historical context of this connection. Because one thing that is often missed in the computer science community is that this connection is very old. It started a long time ago, and this connection is responsible for some results that you guys already know, that you maybe don't know that came from statistical physics. So I think it's very important when we talk about this connection to remember its history. And so for this educational purpose, I'm gonna spend a lot of time trying to motivate the connection and trying to go through the history. So that's gonna be quite light, you know, not a lot of maths, but you know, I think it's very important. So once I'm done with that, and that should take me maybe half of today's lecture, maybe the full today lecture, then we are gonna start looking one problem that comes from physics, which is about phase transitions between paramagnetic and ferromagnetic states in the Curry-Weiss model. So I'm gonna try to motivate this as a computer science problem, although it's a very simple computer science problem. But the reason I'm gonna do that first is that everything that we're gonna be speaking about later can be understood in this very simple model in full detail. We can actually do all the computations, we can compute everything, and we can understand all the notions that are gonna be important later. Because as we move away from the Curry-Weiss model towards like a more computer science, like real computer science problem, things are gonna get much more opaque and much, much harder, let's say, to get intuition from. And then it requires a bit of time to digest these techniques. So I don't expect you to go out of here like understanding fully these techniques, but we're gonna go through a full computation, and hopefully by understanding everything very clearly at the Curry-Weiss model, the second part is gonna be a little bit more intuitive, although it's not, I appreciate that it's not gonna be intuitive the first time you're gonna see this. And then once we develop like this technique, the idea is, as I said, to try to connect like how to use this technique to address some, like, let's say, more recent problems. And here I have 2 case studies. One is from machine learning theory, which is all the phenomenology of benign overfitting that we can derive from this statistical physics point of view, and double descent benign overfitting. And the other one is about typical case computational complexity. So trying to establish computational to statistical gaps in some inference problems, inverse problems. Okay, so that's the plan towards the end, to have these 2 case studies based on the techniques that we're going to develop in the lecture. Yeah. Yeah. Let me see if I can get rid of that. Okay. Good. Thanks. Okay, so let's start. So as I said, like we're going to start with this historical introduction, and one of the things that I want to first try to motivate to you is what is a glass, because you're going to often be speaking about spin glasses and disordered systems, and so I want to motivate like what is a glass and how is a glass is connected to problems in computer science. So if you took a physics class, one of the main ideas in statistical physics is that the goal is trying to describe macroscopic properties of a system. So let's say the table or like water and so on through its microscopic properties. So you start with the microscopics, like you start with an energy function that describes a cost function on a system of particles, and then you want to see something like what is this system is going to be at a certain temperature. So it's going to be water or it's going to be ice. And one of the ways that you describe phases of matter, like whether it's a solid or a liquid, is typically through some symmetry on the system. So for instance, one way you describe a liquid is a system where, let's say, you have a density of particles, and this density is well defined, and let's say it's translational invariance. So you have like this thing that if you look and you translate a liquid, it still looks like the same liquid. And you can define a density, and this density function is translation invariance by any like continuous translation. So there is this idea of like trying to classify phases of matter by symmetries on the microscopic level that translate to the macroscopic level. And so a solid is also a system which is translation invariant, but you don't have translation invariance over all continuous translations, but rather discrete translations. So you can describe the difference between a solid and a liquid by the break of a continuous translational symmetry towards a discrete translational symmetry. And the solid, you see like the way we like to think about solids is like you have a lattice and you have like the molecules of the solid are organized in a geometrical way in this lattice, and the translational, discrete translational symmetry is the symmetry of the lattice, underlying lattice. And then you can describe this transition between solid and liquid by varying a parameter, and you can say, okay, there is a critical temperature above which this symmetry is broken. So that's kind of one of the main ideas in what we say like Landau-Ehrenfest like classification of phase transitions is this idea that you can classify the system by defining order parameter. So here the order parameter is the density, and then the density satisfies certain symmetries, let's say translational symmetry. And then if you have like continuous translational symmetry of the density is constant at anywhere in the system, that's a liquid. If the density is constant like at every discrete, let's say, translation, then this is a solid. So that's one way of classifying things. And then once you have this energy function and you have this order parameter, you can try to make a plot. And this plot is usually a plot in some kind of space of energy on the space of the order parameter. So the order parameter usually is a macroscopic quantity. So it's a quantity that summarizes the state, like a macroscopic state of the system. And so in this plot of the order parameter, so for example, here you can think about the density against the temperature. You have this energy, we call this an energy landscape. So this is going to be a curve. Of course, here is in 2 dimensions, but you can think this as being in as many dimensions that you have order parameters. So let's say you can have the density, you can have also the pressure, and so on. So this is just a schematics. I don't want to say that this is like the phase diagram, let's say, of a specific liquid or so on. So actually, in this case, it is of graphite, arrangements of atoms of carbon. And then in this landscape of the order parameter against the temperature, you're going to have some minima. And the idea is that each of these minima corresponds to a stable phase of the system, a stable phase of matter. And the phase that you are is where, in which minima you are of this system. Of course, the system wants to go to the global minima, the one of minimal energy in this space. So here, if you go for carbon, you're going to have the minima is going to be graphite, like the global minima is going to be graphite. However, since this plot is not a plot on the space, the microscopic states of the particles, but rather is a plot on the macroscopic state, like let's say the density. If you change just one particle, the density doesn't change a lot. So actually, to go from one minimum to the other, you need to change the configuration of many particles in the system, so you can have a change on the order parameter, which is order 1. So what happens is that if your system happens to be in one of these local minima, jumping one of these barriers to go to another local minima, let's say to go to the global minima of the system, might take a very, very large number of changes in the microscopics of the system. And this means that the system gets trapped into this local minima. So one way of thinking about this is, let's say you have many carbon atoms, you heat them a lot, so they are completely disorganized, they are like a gas, and then you start to cool it down. And as you cool it down, the system is gonna try to go into one of these minima, like to organize into a phase, which is gonna be the phase corresponding to the first minima it hits as you cool down the temperature. And depending on how you cool down, you might end up in one of these different minima. So you might end up in diamond, or you might end up in graphite. And as you know, graphite is very different from diamond. And the fact that to go from graphite to diamond requires, let's say, many rearrangements of particles that actually will take exponential time in the size of the system to happen by just like fluctuations, statistical fluctuations. This means that actually if you end up in diamond, you're gonna be stable. So that's what we call in physics metastability, is that even though it's not the global minima, the state of lowest energy, once you end up there, because it's a local minima in this energy landscape as a function of the order parameter, you stay there. So that's what we call metastability. And that's a very important concept here. We are gonna see this very explicitly in the Curry-Weiss model, but essentially the idea of metastability is behind what makes like a system computationally hard. Because if you think about like an algorithm that is trying to start from, let's say, a random configuration and go down to the global minima, and is making only local moves, updating, let's say, the weights of a neural network locally, the fact that you have this local minima on the space of parameters means that you're gonna get trapped in one of these metastable states and you're gonna stay there. And the fact that it's not the global minima means, let's say, that you have bad generalization, or not, let's say, in a computational system. And jumping this barrier requires so many moves that essentially in the size of the system that if the system is very large, you are in high dimensions, you're gonna stay there and you're gonna get trapped there forever under a local algorithm like gradient descent. So really the notion of computational complexity coming from statistical physics is gonna come from the fact that you have these metastable states, local minima in this energy landscape as a function of the order parameter. So okay, I think that's very abstract for now. And if you are not used to these ideas in physics, maybe you are confused at this point, but I promise you we're gonna see this in a very concrete example where you can compute everything. But for now, I want to have this, like, let's say, more high-level discussion of these concepts. Are there any questions about this? Yeah?
Diamond and graphite, but is there like 4 local?
Yeah, so for example, in carbon, so in this specific phase diagram, there are 4 local minima. You can end up everywhere. You can also end up in graphene, which has certain properties that are very different from graphite, and also very interesting properties, as interesting as diamond, let's say. Maybe, I'm not sure if as expensive as diamond, but as interesting as diamond. Yeah?
So what is the x-axis?
So the x-axis, so here it's something specific about the system. My goal is not to go into the physics of carbon, but the x-axis is gonna be some kind of, so here is gonna be some kind of potential, some energy function, and here is gonna be the order parameter. So in the example that I was giving about liquids and solids, let's say it could be the density, it could be something like the magnetization of a spin model. In the case you're going to look concretely, it's going to be the magnetization. But you can think about it as being like some order parameter. So here I'm not saying what it is on purpose because it's not the goal here to understand like the physics of carbon. But you can, by the way, it's not always a two-dimensional space. You can have like a space which is 3, 4, 5 dimensions. But one thing which is important here is that the space of order parameters are usually macroscopic quantities. Quantities that depend on many molecules of the system. So it's gonna be lower dimensional than the space of configurations of the atoms of the system. Or if you want to think about a neural network, let's say you have the space of all possible weights, and the order parameter is gonna be something which is a statistics of the weights, an aggregate of the weights. So it's gonna be a lower dimensional space that is gonna identify which state, which phase the neural network is gonna be. And again, this is gonna be very concrete in the Curry-Weiss model, but here is just like a more of a high-level discussion. Okay, so let me show you one very, let's say, concrete example of a metastable system, which is a supercooled liquid. So I'm from Brazil, and in Brazil, it's very hot, as you know. Like, okay, not all of Brazil, but I'm from Rio, and Rio is very hot. And so we drink cold beer. And when I say cold, it's really cold beer. Like, when you choose a bar where you're gonna get your beer, actually the bar has the temperature of the beer like on the outside. So you can choose the bar that has the coldest beer, okay? So that's very important for Brazilians to choose like the place with the coldest beer because it's very hot. So beer freezes at -4 degrees. So it's slightly lower than water. And so the bar wants to be very close to -4 degrees. The problem is that if you are at -4, which is the critical temperature, small variations of temperature can make the beer go from liquid to solid, which you don't want. And that's very important, and the waiters understand this very well, because if they freeze the beer while they are opening, because when they open, they disturb the system, and the system that, you know, solid is one minima, and liquid is another minima, but if you're close to the critical temperature, a small jump between the two can go from one phase to the other. And by opening the beer is enough energy that you input in the system so that you can make this jump. So the waiters, they are very careful when they open the beer, because if they jump, they have to pay you another beer from their salary. So all waiters in Brazil kind of understand metastability very well, and I'm gonna show you this. So here you have a beer, is in -4 degrees, and just by tapping, the beer like transitions from one phase to the other. So that's metastability in practice, okay? There is some space, and in this space there are two minima. These minima are close together, and by tapping, you just made a jump and you cross from one phase to the other. That's bad for beer, and that's actually going to be also bad for algorithms. And that's the point we're going to try to make later. Okay. Now, if you think about a typical physics system, let's say water, you have 3 phases. You have gas, vapor, you have liquid, and you have solid. So this landscape, this energy landscape, is very simple. You know, there are 3 possible, like two possible minima, 3 possible minima maximum. And each of these phases correspond to one of these states, depending on the temperature of the system. And they are very well described by another parameter that we understand very well, and so on. Now, what is a glass? A glass is a system that has, let's say, a hybrid between let's say, a solid and a liquid. It's a system that is in a disordered state, which is frustrated. If you think about this notion of each of these minima being one phase of matter and having several minima as metastability, one way of thinking about the glass is about thinking that there are many metastable states. Many minima in this energy landscape. And that's very unusual. And where this comes from, so one way of seeing this, for instance, is about sphere packing. So if you imagine having like spheres of different sizes. So let's say you have spheres of different radius, and you have small ones, you have big ones. And then you throw them in the table, and you try to pack them in a configuration that is as tight as possible, okay? So if the spheres were all of the same size, that would be easy. You just like put them in a geometrical way, and you'd have a solid. You have like some kind of a geometrical arrangement of the molecules. If the spheres have very different sizes, very small and very big, likely when you try to pack them together, it's going to be very hard to find a state which is very tightly packed. You're going to have like some regions which are empty with a small one, and this small one can be fit anywhere. And moreover, if you look at how many configurations, like how many ways of organizing the particles that give the same kind of tightness, there are going to be many configurations that have more or less the same tightness. So the system, what we say in like physics language, the system is frustrated. So there are many, many configurations of particles that have the same energy, and that's why there are so many minima, because all of these minima have the same energy. And the system is not a solid because it's not geometrically organized. So the density is not like translation invariance by discrete translation. It's not a liquid because the density is also not translation invariant against a continuous translation. There is a profile of density. When you look at the density of a square and the density of another square, it's going to be different at every point that you look at. So it's not a solid, it's not a liquid. It's some state that is not the global minima. And there are many, many local minima, and all these local minima have the same energy. So there are infinitely many, if you want, exponentially many metastable states. And that's why glasses have properties which are between liquids and solids. It looks like a solid, but it's not as robust as a solid, and it flows. But it flows in time scales which are much, much larger than the time scales that a liquid flow. Actually, it takes like hundreds and hundreds of years for the windows of the cathedral, like to the vitrals of the cathedral, to actually flow. But they eventually flow, and you can see these in like medieval cathedrals that glasses actually flow. So if you look at the energy landscape of glasses, that's how they look like. They have like many, many, many minima, and then once you go into a minima, there are many, many, many minima inside this minima, and so on. So they have this kind of what we call glassy structure, like very, very disordered energy landscape. And that's why back in the 80s, when people were thinking about doing statistical mechanics for glasses, people were very confused because the theory of phase transitions by Landau and Ehrenfest that classifies these minima in terms of like, local minima of an energy landscape was not very well adapted to the situation. You have like exponentially many minima. The tools were not very well adapted, and people were trying to make theory, but they were facing like a lot of challenges. So they would try to make an approximation here and see that actually doesn't match experiments and so on. So there were many open problems back in the 80s on trying to understand what is the right framework to look at these systems that have exponentially many metastable states. And that's where comes Giorgio Parisi, because Giorgio Parisi was one of the first that solved this problem and developed the framework, the toolbox, to try to analyze this sort of problems where you have glassy behavior. When you have frustration, you have many metastable states. And in the description of the Nobel Prize is interesting because they say that the work of Giorgio Parisi makes it possible to understand and describe many different and apparently entirely random materials and phenomena, not only in physics, but also in other very different areas, such as maths, biology, neuroscience, and machine learning. And they speak specifically about the connection with machine learning and computer science. So that's actually interesting because if you talk with a physicist that worked in glasses and spin glass physics, you'd say, it's crazy. The Nobel Prize will never give a Nobel Prize to a field such as glasses because even though the theory of glasses no one had understood before Giorgio, it's kind of not so useful because people have been making glasses for years. They understand very well the properties of glasses. So Venetians were making very, very beautiful and like nice glasses. In the 80s, people could make glasses which are hard. People can make glasses like, which they have like high isolation, like double glazed windows, and they can make very resistant glasses like the glasses of the cars. So people understood how to make glasses, even though people didn't understand the theory of glasses. So let's say the scientific endeavor to try to understand like the physics of glasses is very nice, but not very practical. So people were saying, he will never get a Nobel Prize because there is no practical application of this kind of stuff. And however, it turns out that the theory that he developed to understand like actually real glasses also can be applied in other fields. Fields where you have the same idea of frustration and you have the same idea of metastability and so on, like computer science. And I think a lot of us in the community believe that one of the reasons why he got this Nobel Prize is exactly because of these connections where the theory that he developed for structural glasses actually applied for other systems, let's say computer science, biology, and so on, weather prediction, where you have the same kind of glassy behavior. And here you have actually a practical application and a practical impact. So I think that's a very beautiful story of how a purely intellectual endeavor in research, which doesn't have any, let's say, important practical application, eventually ends up being very useful in a field that started to grow like, in the 80s, 90s, and then nowadays exploded, and they rewarded Giorgio for exactly like creating the framework that allows us to understand other problems than only glasses. Later on, so Giorgio developed all these ideas in the 80s, but later on, Talagrand, trying to make sense of these physics ideas, like trying to put them on mathematical rigorous footing, got awarded the Abel Prize. And the description of the prize says that Talagrand uses his knowledge of statistics and probability to prove limits on how spin glasses matter can behave, and thereby completed the proof for Giorgio Parisi's Nobel Prize winning work. So here is another point of view of the same story. They're saying that all these ideas that Giorgio developed, trying to make them rigorous, develop a lot of new mathematics. So if you are a mathematician and you're looking for interesting problems and interesting things to prove, these ideas are also a great source of open problems. So there are many open problems. I can tell you about many open problems, both coming from spin glasses or the applications of these ideas in machine learning, which are still open and are great PhD projects. So, you have motivation from either like, the physics or the maths to study these topics. So all of these ideas of Talagrand are very well summarized in this book, Mean Field Models for Spin Glasses. And I want to give you just a extract of the book because it's quite fun. So he proves this formula, which is called the Parisi formula for what is called the SK model. And then he says, okay, where log x denotes blah, 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 the natural logarithm of x. Of course, you should rush to require medical attention if this formula seems transparent to you. And then he goes on into like deriving this formula from principal mathematical ideas. So yeah, that's I think it's a quite fun book to read if you like high dimensional probability. Okay, so I have tried to motivate this connection between glasses, like frustration in materials and frustration in other fields. Let's try to have a look at problems which are glasses, but which are not physics problems. So one of the first problems that was studied in this connection is what is called the traveling salesman problem. So which is the following. So given a list of cities and the distance between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? Okay, so that's if you are from computer science, that's a very well-known problem. And I guess that speaks a lot to you, much more than molecules in a box and so on. So this is a very, very important problem in computer science. It's an NP-hard problem. And this was the first problem which actually physicists tried to understand, and that made the first, let's say, one of the first bridges between computer science and statistical physics. And this is a seminal work that was published in 1983 by Kirkpatrick, Gallant, and Vecchi. And if you look at the paper where they developed this, they say in the first lines of the introduction. So the analogy between cooling a fluid and optimization may fail in one important aspect. So in ideal fluids, all the atoms are alike, and the ground state is a regular crystal. So that's exactly what we were talking before. So you have two phases. You have the minimum energy state is a solid, which is a crystal, let's say ice. And then if you increase the temperature, it transitions from that to a fluid. And you just have these two states. However, a typical optimization problem will contain many distinct, non-interchangeable elements. So a regular solution like the crystal is unlikely. Regular meaning symmetric, like translational symmetric, for example, in this example that I gave before. So the physical properties of spin glasses at low temperatures provide a possible guide for understanding the possibilities of optimizing complex systems subject to many conflicting or frustrating constraints. So constraint satisfaction problems, like the travel salesman problem, where you have many cities, and you have many constraints because you have to pass over each city at least once, and you cannot repeat the city, and you have to come back to the first city. So these are constraints. Is a problem on a graph, is a discrete problem, non-convex problem, and finding an algorithm that efficiently find this path is going to be very hard because you have many variables, many constraints, and hence, if you assign a cost being, let's say, repeating the same city twice, you pay a price, the energy landscape of this problem is going to have many metastable states, many local minima, which corresponds to states in which, let's say, you go for the same city twice, but can be any of the cities if the cities look more or less alike. So the energy landscape of this problem should be very glassy. And this is like a computer science problem where you also have the same picture as like the glassy energy landscape. And they went on and they used an idea that came from physics, which is called annealing, which is, okay, whenever you have many local minima, one idea is that you can start at a very high temperature where there's only one minima. Like, you can imagine like this energy landscape, let's say many valleys, and you can imagine, let's say, something like this, and then you have something very glassy. And then you can say, let's start at high temperature. So high temperature means that I start somewhere here. And so if you start at this energy and you look at this, let's say, imagine like the temperature is filling the water on this minima. So you fill the water, and so if you are going to jump and swim in this lake, the lake just looks like a big lake, right? It's like a convex problem. You just can swim, all directions look the same. As you lower the temperature, when let's say you hit this one or this one, you start seeing several small lakes. And as you go down and down in energy, there are more and more lakes. Eventually, when you are at zero temperature, you're going to see all these very small glassy lakes. So one idea in physics is to exactly try to use this as an algorithm. You start at very like a random state, a very high temperature, and you start lowering, you start optimizing, like doing, like, let's say, gradient descent at lowering temperatures. And this is what is called in physics like annealing. And the algorithm that they developed is called simulated annealing. So maybe, okay. Yeah. Okay, good. So I can show you how the algorithm looks like that they propose in this paper. Yeah, here. So you can see there, like, as you lower the temperature, you're going to end in one of the minimas. And so this idea, like, gave this algorithm. And one thing which is very interesting is that before convolutional neural networks, so before the seminal paper of Yann LeCun, which is one of the most cited papers. Now I don't know anymore if if Adam has more citations than convolutional neural networks, but okay. Before all of that, before convolutional neural networks, this paper by these three gentlemen was the most cited paper in computer science. And this is an algorithm that comes directly from statistical physics. So I think it's very, very, very nice because it illustrates first that this connection is old, so it dates as far as 83, and it's not only about like, you know, doing some theory that has no relevance. You can actually use these ideas to develop like algorithms that are used in these combinatorial hard problems. Okay, so let's move on time. So more or less at the same time, in 1982, John Hopfield started thinking about the problem of modeling memory in the brain. So he was interested in this problem of what is called associative memory, which is the following question. So you go through your day, you see many things, you read a book, and then you sleep. How is the information that your brain absorbed stored in the brain? What is the process in the brain, like what goes on in the level of the neurons, such that the memories are stable, or some memories are stable in your brain? What could be a model of, let's say, particles or neurons that interact among each other that is going to have like some stable storage of information? And so this is thinking about neural networks, but not artificial neural networks, like biological neural networks. And the way that John Hopfield went on to model this problem of associative memory is using exactly this idea of the energy landscape. So he thought the following, it's like, okay, if I can build energy landscapes where the minimum of the energy landscape is a memory, because in this space is very stable, these are metastable states, so they are stable. If I can store information in this minima, then they're going to be like stable information in the brain, in the system. So he used this idea in an inverse sense. So let's say using the metastability as a way of storing information. And then he went on to develop what is called the Hopfield model, which translates this idea to maths. And you can see like here one example about the Hopfield model. So I'm not defining the model, but here let's say you have like a picture of a bike. So it's quite old-fashioned because the paper is quite old. But you see you have like a bike, an image of a bike, and then you store this image of the bike in the Hopfield model, in this neural network, and then you give some noisy version of the image, and what the system does is that it finds the minima which is closest to this initial state, which is the noisy version of the bike, and if it is not very noisy, what happens is that you end up finding the bike. So you can do denoising with associative memory. And that's one example. So that's quite cool. So a little bit later, like 3 years later, these three physicists, Amit, Gutenfrand, and Sopolinsky, they went on to actually connect this model that Hopfield had introduced to some of the techniques that Parisi had developed for spin glasses. So they said, okay, this landscape you can understand as an energy landscape of a statistical physics system, and we can use the tools of statistical physics to actually analyze. And the question that they analyze in this paper is, how many memories can you store in a given Hopfield network? Because, you know, the network has a capacity, and you cannot store like infinitely many memories, otherwise the network might lose information. So they went on to try to ask this question: what is the critical threshold, let's say, of memories that I can store in a network? And that was the first time where they connected the ideas of spin glass to a neural network, a biological neural network, but a neural network. So they went on to use ideas that were developed in the context of spin glasses, and in particular, this is one of the main references in spin glasses, is the book of Parisi, Mézard, and Virasoro, and they went on to compute this curve. So alpha is the number is the number of memories per dimension. So let's say n over d. And here is the number of errors that you make in retrieving your memory. And they saw that above a certain threshold, which was 0.138, there is a transition above which you cannot retrieve any more memory without making random guessing error if you were trying to random guess. So this transition here is a phase transition. Again, this is a problem where you have like many variables, dimensions, many constraints, the memories that you need to store, and above a certain threshold, above a certain number of memories, you cannot retrieve them anymore because of this energy landscape. Okay, so the reason I'm showing you this paper, because this is, as far as I know, one of the first papers that established on a mathematical level this connection between spin glass physics and neural networks. And this work drew a lot of attention of a lot of physicists, and from that moment on, from 85 on, a lot of people doing physics jumped into this field because they saw, oh, look, so many interesting problems in constraint optimization problems, in discrete optimization, in computer science. We can say something because we can connect these two things. Let's work on that. And physicists started jumping into this field. And here I'm showing you like a workshop that was organized at the École Physique des Ouches. So for those of you who know, Les Ouches is a very important venue for theoretical physics. It's in France, it's in the French Alps, and people can organize schools there. And in 85, there was this school that you can see the list of participants, so there are a lot of participants, but you can see people like Mézard, Hopfield, Virasoro. So Mézard and Virasoro are two of the researchers that wrote this book with Giorgio. So you can see John Hopfield was there. And then, interestingly, you can see computer scientists that were there as well. So one of them that I'm highlighting here is Ian LeCun, which I guess you know very well. And in his book, he quotes like the following, he remembers like this school saying that, at 85, only physicists were interested in neural networks. And my professional life truly shifted in February 85 during a physics symposium at Les Ouches. There I met the crème de la crème of international research interested in neural networks, and I gave my very first talk in English. So it's interesting because he was a young graduate student that was like one of his first schools, and was a school exactly in the intersection between statistical physics and computer science. And they were talking to each other, and they were doing progress together. And as Ian says, like at this time, was mostly physicists that were interested in these questions. And by the way, if you go on the book, he also says that, after finishing his PhD, he moved to Bell Labs, where he would develop CNNs. And the person who hired him in Bell Labs was in the audience in this school. So there's also like a very interesting contribution of Les Ouches to the history of computer science. So there's other people that you might know that were there as well. So here, there's one paper by Personnaz, Guillon, and Dreyfus. And Isabelle Guillon, maybe you know her, so she's very well known for having developed many of the ideas on support vector machines. And she quotes into this blog post, remembering this school, so I benchmarked neural networks against kernel methods with my PhD advisor, Gérard Dreyfus and Léo Personnaz. And the same year, two physicists working close by, Marc Mézard and Werner Kraut, published a paper on the optimal margin algorithm called mean-over, which attracted my attention. But it was not until I joined Bell Labs that I put things together and we created support vector machines. So here, another example of the impact of this interaction between physicists and computer scientists. 85. Finally, I want to tell you about one or two last papers, which are also seminal papers in this field. So I told you that Hopfield was one of the first to make connections between the statistical physics and biological neural networks. So this is the first paper that made the connection between artificial neural networks and statistical physics. So it's a paper by Elisabeth Gardner and Bernard Derrida. And here they ask the question, if I have a linear classifier, how many random points can I throw in space such that I can perfectly classify. In modern language, we would call this interpolation. So how many random points in a space I can throw before I cannot anymore find a perfect interpolator of the points. So they used again like the methods of statistical physics that we're gonna see later, and they drew up this curve. So kappa here, or K, is the margin. So you can consider the problem with a generic margin. So you can consider a classifier and say, I want to perfectly classify within a margin, kappa. And they computed how many of samples per dimensions you can store before you start like actually making mistakes. So for kappa equals to 0, this is 2. For kappa equals 0.5, that's 1, and so on. And that was one of the first times that these tools were used in, let's say, artificial neural networks. And from that moment on, I could, give the whole 5 lectures about the papers in this field, because it started like, a wave of papers in this field in the physics community. So, I could spend hours and hours going over what went on from 87 to 95. And this is all much before like what we would call today like the machine learning revolution. This is all in the period where some people call like, the AI winter, where no one was believing in neural networks, but physicists were interested in this problem just because they were interesting problems. Like, finally, let me show you last 2 papers. This one in 92, which is about neural networks and the bias variance dilemma. And this is a paper by Stuart Geman and René Dursault and Ellie Bienenstock. So these ones like in Paris, like they are my neighbors near École Normale. And they were one of the first ones to observe that actually, if you start increasing the number of hidden units in a neural network, you didn't necessarily start to overfit, to actually lose generalization as you increase the size of the network. And they said that's weird, because this kind of goes against some statistical intuition that we have about interpolation and overfitting and bad generalization. And in 91, you have one of the first papers that actually studied this in the context of linear regression and observed what we nowadays call double descent phenomena. So they computed the generalization error for a linear regression problem, and they saw that around what we call the interpolation threshold, the error diverges, but then it goes down again. So that was a paper published in NeurIPS 4 in 1991, and again, 2 physicists working in the Niels Bohr Institute in Copenhagen, and NORDITA, which is the Institute for Theoretical Physics. We are going to see this more later. So, okay, so that's more or less the end of what I wanted to get into terms of like this historical overview of seminal papers in this field. And I just want to mention that, this idea between using statistical physics and using physics like to understand these problems was not something that was only like cooking in the physics community, but also some statisticians and some very important statisticians were also thinking about these ideas. And so here I want to bring up like this paper by Lew Breiman. So Lew Breiman was a very important statistician working at Berkeley. And so if you don't know him, he essentially created many of the classical statistical methods that we study, like random forests, bagging, like all of these things he had studied, like boosting. And in 1995, he wrote this very, very, very interesting paper. So if you haven't read this paper, I highly recommend that you do. It's a very, very fun paper to read. So in 1995, it's called Reflections After Refereeing Papers for NIPS. So at the time, NeurIPS was called NIPS. And it's a paper about his thoughts after refereeing, okay? So I guess that all of you that refereed for NIPS have thoughts about it. These are his thoughts in 95. So our field would be better off with far fewer theorems, less emphasis on fetish stuff, and much more scientific inquiry and engineering. but the latter requires real thinking. For instance, there are many important questions regarding neural networks which are largely unanswered, and there seem to be conflicting stories regarding the following issues. So why don't heavily parameterized neural networks overfit the data? What is the effective number of parameters that we need to fit a given target function? Why doesn't backpropagation, so training neural networks with descent-based algorithms, head for poor local minima? And when should one stop backpropagation and use the current parameters? So early stopping. So what is the optimal stopping time? So mathematical theory is not critical to the development of machine learning, but scientific inquiry is. So this idea that maybe we should stop worrying about proving theorems and doing a mathematical theory of machine learning, but rather think it as a scientific problem, trying to do a theory of machine learning that tries to explain what is going on, is if you did any class in physics, that is going to resonate a lot like physics for you. And so he goes on into the paper. So the paper has about 5 pages. And at some point, he defines what he means by inquire. So inquire is sensible and intelligent efforts to understand what is going on. For example, so mathematical heuristics, simplified analogies like the Ising model. So here, very clearly what he was thinking about. Simulations, comparison to methodologies, devising new tools, also theorems, but when they are useful. And then he goes on and says rare. That's not me saying. And shunning panaceas. So okay, I want to end up like this historical introduction here in this paper of Bryman. So do you have any thoughts or any questions about this, let's say, historical overview and thought-provoking message from Liu? You can make comments as well, or yeah. 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 Yeah.
So okay. So I'm a mathematician, I'm a statistician. Like when I think about simulated annealing, I would, I guess, describe the reason it works as follows. Maybe I'm confusing metropolis here. But like, okay, if you're trying to find the minimum and you just keep going, like you only move if you go down, obviously you get stuck in a optimal optimum. But what I would say, I guess, like these algorithms, like the innovation, right, is that sometimes you'll kind of randomly move to a worse spot, right? And this is actually what allows you to like kind of hop these.
Yeah.
So how do I like rectify this sort of just mathematical understanding that's like, okay, instead of only making the decision to move down, sometimes I might like randomly just say, okay, well, let's go to a worse position with like that picture you have.
Yeah. No, so that's a great question. So let me make here the difference between 2 algorithms. So one would be, as you said, like Metropolis, or if you want to think about a continuous problem like Langevin, which would be going down in energy. You try to go down this loss landscape, and then you add a bit of temperature so that eventually there's going to be a fraction of times where you might go into a different direction. And then you might be able to jump one of these minima. The problem is that since this is a local algorithm on the weights, even with this small probability of doing like, a random move in a different direction, because these minima, they are minima into this ordered parameter space, like which is a macroscopic space, this temperature is not going to be enough for you to jump with, let's say, finite probability one of these minima. Because the minima is kind of macroscopic in the number of parameters. You have many of them. So the probability, like let's say the time you take to jump one of these minima is exponential in the size of the system. So that's what we call in physics the Arrhenius law. So Arrhenius or Arrhenius, I don't know how to pronounce properly his name. Actually I don't know where he's from, but never mind. So you would have something like exponential, let's say, let's say you want to jump like, let's say this minima here. So you have like delta E. So the time it would take is something like exponential of the size of the system, let's call it d times delta E. And eventually, if you run for long enough, Langevin, we know you're gonna thermalize, and you know that you're gonna, but the question, of course, is how much time? And if you have this kind of metastable states, the time it will take is like, exponential in the system size. So that's one algorithm. Then the other one, which I would say like more simulated annealing, is to take this idea to an extreme where you'd say, okay, at very high temperatures, like if I put very, very high temperatures, like, so I'm gonna really be able, I'll be really doing kind of a sampling from the uniform measure. Like, I'll be anywhere here. I start anywhere here. And
Like, yeah, going outside of like the, like,
exactly,
you go, like,
exactly. So the way I like to think is that imagine again, like this is water, and you have like this water level. Very, very high water level means very, very high temperature. So at this water level, the landscape is essentially convex. There's no local minima. There is just a huge lake. And then let's say your descent algorithm just jump in the lake, and then now you can swim everywhere in the lake freely. Now, as you lower the temperature, you start seeing the minimum. But what happens, which is the kind of, I think, key intuition, is that like as you lower the temperature, you're seeing more and more minima. So first you just see two minima. Let's say at this temperature here. Let me see the red one. So at this temperature here, now you have two lakes. You have this lake and this lake. And now, if let's say if you are swimming this lake and you lower the temperature, and then when you cross here, you are in this side, you are here, and while you are also here, and the probability of being in each of that is kind of the volume of the lake in each of these ones. And now you fall into one of the big minima. And then you lower more the temperature and you repeat this. And the idea is that if you are lucky, you will always be in the lake that has highest volume, and this will lead you towards the global minima. Of course, it doesn't always work. It's not that any glassy problem, if you do simulated annealing, you eventually converge to the global minima. But you leverage this idea that you lower the temperature, and of course the key question is how fast to lower the temperature versus number of steps. But if you find a very nice schedule, you increase your probability of being in a good basin of attraction. And this is very different from Langevin, which would just like go down and then a little bit of a random move around, local random move. Here is kind of you can try to think about it as a global random move. But it's not exactly, like the connection is not one-to-one, but yeah, great question. Like, yeah.
So it's what you just described, simulated annealing.
Yeah. So that's the main idea of simulated annealing. And by the way, let me make a comment about the terminology. So in physics, like annealing is really what you do when you prepare a system, right? Like imagine glass. Like if you go to Venice and you go like to the place where they do glass, like they literally like heat very, very high temperatures, like sand and so on, and melt the glass. And so the glass is completely disordered, like, right, it's liquid. And then you cool the glass, but you cool in a very specific way. They do all these things and they blow and there's some water and it's a very impressive thing. But this is annealing, like this is actually cooling the system in a specific way such that you are in the good minima. Or, they are trained, they are artisans, and they train for life so that they produce the property of the glass, the state of the glass, which has the good physical properties. Let me mention another example, which this is a very cool example, is chocolate. So chocolate, chocolate is not like, it's a mix of materials, but chocolate is solid and is in one crystalline state, which is essentially governed by the crystals of cocoa butter that crystallize when you lower the temperature. If you increase the temperature in chocolate, it melts and becomes liquid, right? Now there are six minima, 6 crystalline states of chocolate that are different, have different energy. And they have very different physical properties. All of them look like chocolate, but they have very different melting points. And one of them melts, let's say at 20 degrees. I'm just cooking up a number. So this crystalline structure of chocolate, when you put in your hand, just melts because, you know, the melting temperature, it's lower than the temperature of your body. And that's not good because you take this chocolate and it just melts in your hand. So what you want when you make chocolate is to end up in one of the crystalline structures of the 6 crystalline structures that melts in your mouth that has higher temperature than your body. So there is something called tempering in chocolate making, which is you melt chocolate and you mix it in a certain way with a lot of skill. It's not easy to make, such that when it solidifies in the good minima. So that has the good physical properties that you want, which is to melt in your mouth but not in your hand. And all the other crystalline structures are bad structures. And so you might have realized this when you have chocolate in a very hot country, it melted, and then you put in the fridge, or you know the temperature is cooling and you put in the air conditioning, and it solidifies again, but it's not the same chocolate. It's very bad chocolate. It's like, you know, it doesn't have the right properties, the right taste, the right texture. So that's also metastability, and that's also annealing if you want. So yeah, I like that example a lot because it's very concrete. Any other questions? Yeah.
You told us what the glass is, but I trust that you later tell us what is a spin glass.
Oh, right. So, okay. So a spin glass is a glass in the sense that I try to define, in which the energy landscape has infinitely, like, you know, exponentially many local minima. But it's a system that is defined with spins. So spins I'm going to define are like binary variables. So it's a system where the configurations are in the hypercube. And systems in the hypercube that have glassy landscape are spin glasses. So not all glasses are spin glasses, but all spin glasses are glasses.
I'd be like a failure of like my physics education, but I think
Yeah.
this is the first time I realized that like glass literally like flows. It's just like fair.
Yeah. Yeah, I mean, it flows like that. Exactly like that, like in time scales which are exponential in the time of the system, in the size of the system, yeah. Yeah. You can see that actually if you go like very old churches in Europe, like you can actually see that the glass flows.
Or something, you know?
Yeah, that's where I'm going. That's where I'm going. And I guess you're also going there. And yeah. Yeah. So the local minima. Yeah, so that's exactly the intuition, is that at a certain energy level or a certain temperature, which is you put by hand on your algorithm, you can think of it as the temperature being, let's say, Langevin. You're doing gradient descent plus noise, and the noise, the temperature is what you put in front of the noise. So at high temperatures, essentially, if you take, you're sampling from kind of a uniform measure, if you want. So there's no local minima. And then as you go down, you start to see the local minimum. It's not that they, like, the background of this picture, the energy landscape, is the set of extremizers of the energy. And then we like to think about algorithms as being dynamical processes, like stochastic processes, if you want, that live in this landscape. And if you would have no temperature, you would just do descent on this landscape. But as you add temperature, we like to think in physics as starting on an effective landscape, where the minimum of the effective landscape are the lakes at this given energy level. So that's a conceptual way of thinking. So there are two landscapes. There's a landscape at a given temperature, and there is a landscape at zero temperature, which is the background, like the black part. Some lakes will disappear. So well, it depends. If you are here, then you never see this guy because you are kind of swimming here, and as you lower, you're going to just end up here. But let's say if you end up here, and you are at this level, then let's say you just see one big lake here, and then here depends on where you are. You can end up here. But once you are in one of the basins, you don't see the other ones. Like your algorithm doesn't see the other ones because to go there, you will require like, let's say, exponential number of moves. But it is there. I mean, it's just that with a different schedule, you could end up there. But with, let's say, the probability of ending up in this lake is very low because first you have a lot of mass, which is like, here, then more mass here, then more mass here, and then there's more mass here. So the probability that you end up in this lake instead of this one, it's much higher as you go down. But in the worst case, you could end up here. Maybe we can discuss more offline if you want to discuss more this picture. Any other questions? Okay, so we still have 20 minutes, I guess. So, or maybe 10 minutes. So I'm going to start what we're going to do next on the board. So maybe we can switch completely to the board. Yeah, I'm just gonna write down the model they're gonna be studying, and then of course, like next time, tomorrow, I guess, we can go back to it. Just to use a bit of the time that we have. So okay. So my goal now, as I said, is like to give you a crash course on the statistical physics of a very simple model where you can compute all these quantities. So a crash course on statistical physics. Okay, so let's consider the following optimization problem. So I'm going to introduce a very simple optimization problem. That's a calligraphic C. So we want to minimize this quadratic form over variables which live in a certain space, and where J is a matrix. Okay, I'm going to call it D, the symmetric matrix. And the configuration space, it's a subset of RD. So these are variables which are in a subset of RD, and we want to minimize this quadratic form. Okay, so many problems can be put in this form. So note that this problem is quadratic in the variables S, which means that if this is a convex set, it's easy. So for example, let's take one case which is easy, which is this is kind of the sphere in dimension D. Then we all know that by definition, this is just the operator norm of the matrix. So, quite easy problem to solve. But in general, if this is like a non-convex set, in particular, for example, this is like the hypercube, like a discrete set, then minimum of S can be an NP-hard problem. So in general, like having like a discrete optimization problem over the hypercube, even if you are doing like just minimizing a quadratic form, can be a very, very hard problem computationally. So for example, many problems of interest can be put in this form. So the Ising model. So in the Ising model, you have a graph. So you have like J is the adjacency matrix. Of a graph. And then you are minimizing like this quadratic form over variables which are neighbor to each other. So that can be a hard problem to solve computationally, like actually to find the minimizer. Other problem like the max cut problem can be written in this form. Clustering can be written in this form. And many problems on graphs like can be written in this form where the variables live in the discrete hypercube. So, you know, I'm gonna use like this as like a paradigmatic like kind of problem where we can try to understand how to approach this from statistical physics point of view and how we can connect to some of the ideas that we saw in the historical introduction. So the statistical physics approach so in the statistical physics approach, what we are going to do is that we are going to say, okay, we want to solve, let's say, this class of hard or easy combinatorial optimization problems. And instead of looking at the optimization problem per se, we're going to define a probability distribution over what we call configurations. So in the statistical physics parlor, like we call the variables that we are trying to optimize over configurations. And we call this set the configuration space. So configuration is just a set of variables. So for example, here is going to be a set of, is a vector in the hypercube, is a configuration, and the hypercube is the configuration space. So you're going to define a probability measure over the configuration space. So I'm going to try to discriminate, at least in the beginning of the lectures, between like random variables and realizations, as using the typical, you know, big letters for random variables. And these are, just to remind you that in this case, these are vectors. But okay, they could be anything in a configuration space. So you would define this as a probability measure. So there's a normalization. A probability measure of this type. So let's try to unfold what these quantities are. So as we said, so SI, I'm going to call it the degrees of freedom or the spins if SI is binary. So when I say a spin, I just mean like a variable which can take its value plus or minus 1, discrete variable. And in more general physics parlor, like we say that, you know, the elements of the configuration are just the degrees of freedom of the problem. They can be anything, like they can be particles, molecules, like proteins, like whatever, peptides. And then the vector S is the configuration. Then we are going to call C the configuration space. So here is just introducing terminology so that we are in the same page when I say something physicky. Beta is a parameter which is larger than 0. It's called the inverse temperature. So yeah, this is the source of a lot of confusion because in physics we like to think about temperature, and the temperature is the inverse of beta. So, but it's more handy to write beta than 1 over T. Yeah, so you know, low temperature is high beta, and high temperature is beta going to 0. So H is called the energy function or Hamiltonian. After Irish mathematician Hamilton. And ZD, which is the normalization of this probability measure, is called the partition function. And the probability measure itself, we're going to refer it as the Boltzmann Gibbs measure or distribution. So when the configuration space is discrete, this is very easy to define, you know, probabilistically, if you want to be rigorous. If it is continuous, it requires a little bit more of care. But the idea here is not to go into the very much details of the maths behind. So I'm just going to write this as when it's discrete is a probability distribution. When it's continuous is going to be a probability density, and we are going to interchange between the two. But for now, I'm going to try to be very precise, at least for the curve-wise model. Always the configuration space is going to be discrete. It's going to be the hypercube. And the measure is just going to be well-defined because it's a discrete measure over the configuration space. You have 2 to the d configurations. So the number of configurations is exponential in the dimension of the system. And we are defining just a measure over this configuration. The measure is weighted by this energy function, which tells me for a given configuration, what is the weight that this configuration has, what is the probability of sampling this configuration is going to depend on its energy. So, you know, yeah, the larger is this thing, so the smaller is this thing is the exponential of minus. Yeah.
That C is the partition function. So is it that partition function that you input the number, then you output how many possible ways that you partition that number into different numbers that the sum is equal to the number? Or is
it is kind of a volume.
So here it is a normalizing term.
It is a normalizing term, yeah. It is so it's not to do so much with partition in the sense of cutting the space. It's just, you can think just as a normalizing constant of this probability distribution, but it's gonna play an important role later in the physics because it's gonna be closely related to like large deviation principles for this probability measure. Before ending, so since we started 5 minutes late, I guess I have still like 2 minutes. Let me just make a remark and then we end. And then next time we're going to start concretely studying one of these problems. So, so I told you, okay, we are interested in optimization problems. So I gave you one optimization problem here is like minimizing a quadratic form over a constraint set. I say that in statistical physics, we like to think about optimization problems in terms of probability measures over the configuration space, so over the set that constrains our degrees of freedom, our variables. And so what is the connection between these two things? Well, let me make a remark and end here. Is that, okay, when beta goes to 0 plus, so what we call low temperature, sorry, no, high temperature. High temperature. See, even myself, I still confuse this thing. So high temperature. And by the way, don't hesitate to correct me in the board because I often make mistakes in the board. So when this is the case, this probability distribution is a uniform distribution over C. And here you see why it might be a problem. Yeah, when this is not discrete, defining this thing. But okay, for the spins is very easy because you have 2 to the D configurations, so it's just uniformly sampling over these 2 to the D configurations. So when beta goes to infinity, what we call low temperature, in this case, so P concentrates or peaks is a distribution which is peaked on S star, which is the argmean of H of S, where S is in the configuration space. So in particular, when beta goes to infinity, this measure is going to be peaking just the minimizers of the energy, right? So that's very nice because this is exactly corresponding to this type of optimization problem. So example, take S, which is going to be what I'm going to mostly be studying. So take S to be, sorry, S no. Yeah, take S to be in the hypercube. And then H of S to be this quadratic form that depends on these parameters J. So it's a H S of J. Then we have exactly, if we take beta to infinity, we find exactly that the measure is going to be picking the solutions of the optimization problem, okay? So in particular, we can study the optimization problem by studying low temperature behavior of the measure. So that's going to be crucial for the connection. But the whole statistical physics idea is that we are going to use methods from statistical physics to study these measures corresponding to energy functions that correspond to computer science problems. And that's very nice. Let me end here just saying that, the Boltzmann-Gibbs distribution was introduced to study the behavior of particles, of molecules in nature. And physicists, because they were interested in this limit where you have many, many particles and, and particles arranged in solids, liquids, and so on, they had to deal with this problem of studying high-dimensional probability measures because these probability measures are exactly the stationary points of natural dynamics, right? Langevin and so on, they converge to Boltzmann-Gibbs distribution. So they had to deal in the end of the 19th century with the problem of studying high-dimensional probability, okay? And they developed a lot of tools for that. And that's exactly where the connection is going to be with problems in computer science, where high-dimensional probability is always also the natural language to describe these problems. Even though, let's say, the high-dimensional probability as a field of mathematics was developed much later, right? I mean, Lebesgue, I think, was in the 30s, I think. So Boltzmann was a physicist in Germany in the 19th century. So for me, the way I like to see statistical physics is as the study of high-dimensional probability distributions, the study of high-dimensional probability in the end of the day. So any problem where high-dimensional probability is relevant, these methods can be potentially applied, okay? So let's end the first lecture here, and then next time we're going to study a particular example of these problems. Thank you. We have a coffee break now, and maybe I can take questions if you want. Feel free to come here or discuss around coffee.